Calc 12, here we go. We are doing curve sketching today, which is a fairly long process. It's basically like you're a human Desmos, except even more powerful than Desmos because you'll be able to find max and min values and points of inflection and all the other pieces, asymptotes, everything about a graph and more. So this is basically everything you've done since grade 9, graphing forwards, all comes to a big event today. So here we go. Curve sketching is section 5.5 in our textbook. There's 12 questions on there to do. I don't know how many you need to do. To be honest, I would say minimum of 3 of these would be minimum. And then if you did all 12, you'd be a master. So here we go. Because you'll see today it's a long process. It is a 9-step process. So this is what the book suggests as far as the steps. Just to kind of keep you organized. You don't have to do them in this order, but it's just one thing they recommend. So when you're graphing a curve, you always want to do domain and intercepts and symmetry and asymptotes, much like you did in grade 12. But then you're going to add the first derivative for intervals of increasing, decreasing, and max and mins. Second derivative for concavity and inflection points, and then ultimately you'll sketch the graph in the end. So those are your 9 steps. They are long. Some of them I don't do. Symmetry, to be honest, I don't always do because I find it doesn't always help. But if you do it and there is symmetry, it can save you time. And let's go through the process. So here's the example that we're going to do. It is sketching this function, square root of 2 minus x all divided by x plus 1. And we're going to sketch it, check it with Desmos, use all of our techniques to go through it. So let's start this puppy out. Here we go. So, domain. I always like to look at that first. And what you're going to do for domain is basically what x values are allowed. So you're going to look at and say what x values are allowed here, or more importantly, what x values are not allowed. It has a denominator, so here I can see right away x cannot equal -1, and that's either going to be a vertical asymptote or a point of discontinuity or a hole, but because it doesn't have a factor on top, that's going to be a vertical asymptote, which I'll just put a little arrow here. We'll talk about that in a moment. That'll become our vertical asymptote. Also, there is square rooting, and you're square rooting 2 minus x. So that has to be, 2 minus x has to be bigger than or equal to 0. My pen's dying here. So then x has to be less than or equal to 2. So the domain of this function is going to be all real numbers, everything less than or equal to 2, but also x cannot equal -1. So that just helps paint a little bit of an idea where the graph's allowed to exist. Next thing is x and y intercepts. So as you know from way back in grade 10, 11, 12, x intercepts is when y is 0, y intercepts are when x is 0. So if you do the x intercept first to make y equal to 0, you then can equate that to your function. And when you're solving this rational, I would cross multiply. This would cancel out to give you this radical equation, which you can square both sides, solve for x, and you get x equals 2. So there's your x-intercept of 2, 0. And then your y-intercept is when x is 0. And x is 0, you go to the function, plug in 0 for x, and you get root 2 over 1. So your y-intercept is going to be 0 root 2. Okay, when it comes to symmetry, I don't usually do this step, but I'm going to do it just because they ask us to do it. You can do f of -x, so you go and take your function, make your x into -x as you did in the even and odd situation. So f of -x equals, plug in -x here, that would become a positive. So you'd get 2 take away -x divided by -x plus 1. And when you clean that up, you end up with this mess that does not equal f of x, so it's not even. Also, if you factor out a negative, you can't even get that. That also does not equal the negative of the original function. So this is neither. So it's neither even or odd, which makes sense anyway with a square root. Because it's already, you can even see here, it's already asymmetrical. So right away I could have already known that was not even or odd. Asymptotes. So are there any vertical asymptotes? And there is. We know that you're dividing your x minus 1 is a bad spot, so your x equals -1 is a vertical asymptote. You then could also do what you did in the 1 unit and just do the limit as x approaches 1 from both left and right of that function. So you could go and plug a value of 1, a little bit bigger than 1 here. This is going to be positive, or sorry, bigger than -1. So a little bit bigger than -1. This would be positive. A little bit bigger than -1. This would be negative. So this would end up being negative infinity. Plug in less than 1. Sorry, I did that backwards. Greater than -1. This would be positive because this would be like plugging in -0.999. This one here would be negative. That'd be negative infinity. And then horizontal. You know there's a potential for horizontal or slant because you're dealing with a rational function. And if you think about it for a minute, the power of the numerator is kind of a 1/2 power. The power of the denominator is a 1. So because the numerator power is less than the denominator power, I know this is y equals 0. So we got a lot of information here now. So what I would urge you to do is to kind of keep track of all this information, is get a graph ready, and underneath it have your first derivative and second derivative lined up ready to go so we can get that organized. And let's plot some points on here. So we know that 2, 0 was on the graph. There's my x-intercept. My y-intercept is 0, root 2, which is around 0, 1.4-ish, somewhere in that region. That's just my estimate. I can label it if I want. We'll get to that in a moment. And what else do I have? I have vertical asymptote at -1. So -1, I'll be drawing a x equals -1 vertical asymptote right here. And also I got a horizontal asymptote here. And then I also know from the domain, everything bigger than 2 won't exist. So this part of the graph will not even be there. So the graph's over here somewhere. And I also know, just have that here too, is as you approach -1 from the right, it's way up here. And as you approach from the left, it's way down there. So I got a lot of information. I almost kind of have an idea what it's going to look like anyway. But now we're going to get the rest of the information with max mins and points of inflection and concavity. And this is where the longest part comes in. Because now to do these steps, which is the actual calculus finally, I haven't even touched calculus yet, I'm going to take the first and second derivative. And that is the longest part of the process. So take a look at this mess. You may want to pause this. Okay, I'll just zoom in on, can I get a good picture of that there? Let's see. Okay, there's my first derivative work. I went through and did this. My first derivative ends up being this mess. I used the quotient rule. Then to do the concavity, I took the derivative of that again. Just a lot of work. Like, look at all that grunt work there. You want to pause that and go through that. Make sure you can do that. That's the hardest part of the question, in my opinion. It's not that it's hard. It's just really laborious and easy to make goofy mistakes. And there's my derivative for my second derivative. What I did with this, what I advise you, really encourage you to do, before you move on with this, you want to make sure that's right. So what I did was I went to, I'll just show you here. I went to Wolfram Alpha and, whoops, where am I? And I typed in what is the derivative of that function, and just make sure you type it in. I typed it in, and then it gave me the first derivative, which I made sure I could do on my own. I just didn't let Wolfram Alpha do that. And I can also do it with, if I type in second derivative. It takes a little bit of time to think. And then there is my second derivative. And then I knew I was on the right track. Okay, so that's an important step to do. the next thing is now you're going to analyze it. So now we have the first derivative, which we've done all of that work to get to here. And here comes the fun part. We now know to find critical numbers, which we've done over and over and over again. Critical numbers are where the first derivative equals 0, where the first derivative does not exist, or endpoints. Where the first derivative equals 0, because this is so beautifully cleaned up, it's where the numerator is 0, and that would be when x equals 5. Where it does not exist is where x equals -1 and 2, because that's where the denominator is 0. And endpoints would link to the domain, and that would be at 2. Now, a few things about this. First of all, x equals 5 is outside the domain. So that information that came out of the algebra is actually extraneous. -1 makes sense because I've got an asymptote there, but it's not a point on the graph, so I don't have to worry about that being a max and min, but it is a point where increasing, decreasing can change, and 2 is an endpoint in this situation. So what I would do is I'd go to my first derivative test line. I would put on here 2 as an endpoint, also a restriction if you want, it does not exist. I would put 0 on there as a reference, and then -1, which is a does not exist situation. Test my intervals. So I can easily test here. Plug in 0, negative on top, positive, positive, positive. So this ends up being negative. So I know the graph is definitely going to have a negative slope at that in this interval. And then I would also go over here and maybe test like -1000. So this will be negative, positive, positive. And if I plug a negative, that's also positive. So this has negative slope. This has negative slope everywhere. The graph is continually decreasing from left to right. So now, are there any max and min points? Well, this is not a max or min point for a number of reasons, because first of all, the graph doesn't exist there, so it can't be a max or min point. Also, there's no increasing, decreasing change. This endpoint, though, if you think about it, it's going down. This endpoint is going to end up being a minimum. So you're going to have a minimum value at, we already got the point, 2, 0. So that x-intercept happens to be a minimum. So good information. What I would also do on my graph, I would put this information on here as well. There's my undefined. There's my negative slope going down. I'm just recapping it on here. Here's 2. All of this is restricted, like doesn't even exist because of the domain issue. So now I know the graph is decreasing, and I got a minimum right there. Okay, concavity, same ball of wax. I write down my second derivative, which I already got from my work. I'm just copying it from there. Checked it with Wolfram Alpha because this was such a big question. I didn't want to do all this hard work to find out I'm on the wrong track. That's horrible. And I test it almost identically to the first derivative. So where is the first derivative equal to 0? Or second derivative, sorry, equal to 0. Where is the second derivative does not exist? And where are there any endpoints? Well, endpoints are the same as the first derivative. Does not exist are also the same. -1 and 2 are bad spots. Where is it equal to 0? Well, it's where this numerator is equal to 0. So where is x squared minus 10x plus 13 equal to 0? Solve that quadratic equation, which did not factor. So I chose to use the quadratic formula. So there's my -b minus square root of b squared minus 4 times a times c, all divided by 2a. And I got these two values. So I got x equals positive 1.54 and x equals 8.46. And this is out of the domain, 8.46. And there's my numbers, which again, I would go to a number line, my second derivative number line, 0 as a reference, 2 is my endpoint, -1 does not exist. And then I would also plug on there 1.5-ish. So right there, it's 0 at 1.54. And then I have to test my intervals. And I'm testing in my second derivative. So here I would test with or without a calculator. I would test like 1.9. And I'd have to do a little bit of crunching here, to be honest. So if I plug in 1.9 into here, I'd have to think about that. That's a little bit more work, but I could do it. Here I can do it nicely as far as I know that's positive. That's going to be positive. So the whole numerator is positive. Sorry, my denominator is positive. My numerator ends up being, when I plug it into the second derivative in that region, ends up being negative. Let me just double check that to make sure. I'm kind of second guessing myself there. 1.9 squared minus 10 times 1.9 plus 13. Yeah, it is negative. Okay, good. Just had to make sure of that. So that's negative. That means here it's concave down in that region. Then I would plug in here 0. Now that's a little easier. I can see right away that's going to be positive, positive, positive. So it's positive second derivative, meaning concave up. And then I would plug in something down here like -10. And upon doing that, this ends up being negative again, because that's 100. Is it not? So -10. Because this is whole numerator is positive. Positive, this ends up being negative because you're cubing it. So it's a positive divided by a negative, so it ends up being negative, it's concave down. Now, at that point, no pun intended, I've got changing concavity here and changing concavity here. Are both of these points of inflection? Maybe, maybe not. Remember, for a point of inflection, you have to have changing concavity, but the point has to exist. -1 does not exist on the graph, so then this is not a point of inflection. It is a place where concavity changes, but not a point. This point here at 1.54 is a point of inflection. So I would now know, there's my concavity intervals, and I have a point of inflection at 1.54 comma f of 1.54. And the concavity goes from concave up to concave down. And then I would go to my number line again, and we're almost done. It's a long process for one question. So 2 is an endpoint. -1 does not exist. Here's my 1.5. Is my 0. 1.54 does not exist. This is concave down. This is concave up. This is concave down. And now I can go up here and I can get a nice sketch of this. So I know this is a minimum. I know it's concave down and negative slope. So it must be doing something like this. So it's doing something like this. Now I should probably figure out where it is at 1.54. So at 1.54, plugging that in, it works out to be around 0.3, 0.26. So right here it does concave down to there. And there's my value. Okay, so concave down negative. Then it transitions from still negative slope, but concave up. So it must then swing up this way. So it's concave up, still negative slope. And then at that point there, that's just my y-intercept, it still is concave up and negative slope, and it goes towards my asymptote, which we already anticipated. You would have got that already. It's just this little transition there you might not have got. And then over in here, I know it starts here, and it has to have concave down and negative slope again, so it's doing something like this. And again, I'm just sketching it. There was no other points of interest, so I might be off a little bit here. I should probably plug in -2 to see where it is, but I've done enough work in my opinion. And the last step I would do to make myself feel good is use Desmos, which I know could have been done right away. And here's Desmos. So there's the function I typed in. I did all the little data to it to make sure it made sense. And right there is my graph, and I would just make myself feel good by zooming into, there's my little point of inflection right there. And I can see there's the concave down, transition to concave up, and then I feel better about myself that I'm on the right track. And there's my nice little graph. And again, I know Desmos could have done that in whatever, how long was this video? 20 minutes? Could have done it in 10 seconds, but I would not have known that point of inflection. So that's curve sketching. That's the 9-point process. And I hope you're having a good day. Have fun with sketching. Over and out.